Sheena Barreto, and today I'm going to discuss the last topic, which is horizontal alignment. So, horizontal alignment consists of straight sections of the road known as tangents connected by curves, and the curves are usually segments of circles which have radii that will provide for a smooth flow of traffic. And the design of the horizontal alignment entails the determination of the minimum radius, determination of the length of the curve, determination of the horizontal offsets from the tangent to the curves to facilitate locating the curve in the field. And there are types of horizontal curves, and these are simple, compound, reverse, and spiral. But I'm only going to focus my report on simple and compound curves. So, so the curve is a segment of a circle with radius r, which is discussed on chapter 3. And for the case when SSD is unobstructed, r is equal to u squared over g times the quantity of E plus Fs, where r is the minimum radius, u is the design speed, and E is super elevation, Fs is coefficient of side friction. So simple curves or simple circular curves consist of a circular arc of radius r, this one, um, connecting to two tangent lines. The tangents are here, and at the tangent point called point of intersection, or PI, at specific angle of intersection, or I. And the curve starts at the point of commencement and ends at the point of tangency, or PT. And this one, the green highlight, is the deflection angle. Theta is the central angle. This one is for the stationing, and X is offset, or the offset distance. M is the middle coordinate, the distance between the midpoint of curvature and the midpoint of the long chord, while E is the distance between the point of intersection and the midpoint of the curvature. So if theta is the angle in region subtended at the center of an arc of a circle, the length of the arc is given by r theta is equal to L, or L is the length of a curve, and if the degree of curvature is the angle in degree subtended at the center by an arc of the length, then theta is pi times the degree of curvature over 180. So solving for r yields for r is equal to 180 times 100 over pi times the degree of curvature. So what is the degree of curvature? So the degree of curvature is the value that measures the sharpness of the circular curve and is based on either of the two bases, which is the arc basis and the chord basis. And the degree of curvature can be determined if the radius is known, or the radius can be determined if the degree of curve is known. For the arc basis in the SI system, so for every 20 meter length of curve, uh, that would be the degree of curve. So every 20 is equal to 1 revolution, which is 360. So we have D, or the degree of curvature, is equal to 5, sorry, that would be 1145.92 over R. This will be for the SI system. For the English system, for every, sorry, for every 100 feet length of curve, that would be the degree of curve. So 100 feet equal to 1 revolution, which is 360. So we have degree of curvature is equal to 5729.6 over R. So for the chord basis in the English system, the chord definition of R in terms of degree of curvature is based on a chord of 100 feet. So we can solve for R using sine B over 2 is equal to 50 over R, where R is 50 over sine B over 2. So that is for the chord basis in the English system. So for the chord basis in the SI system, chord definition of R of the degree of curvature is based on a chord of 20 meters. So to get the R, we can solve it using sine B over 2 is equal to 10 over R, where R is equal to 10 over sine B over 2. And that is for the SI system. So we already discussed the elements of a simple curve, and now we are ready to derive and determine their respective formulas. So first is tangent distance. We can solve the tangent distance using the figure from the simple curve, where T is here, R. We have an angle of intersection, half the angle of intersection. So since T is opposite to the angle and the radius is adjacent to the angle, we can use tangent I over 2 is equal to T over R, and T is equal to R tan I over 2. Next is the middle ordinate, where it is derived from the figure where R minus M is here. This is R and this is I over 2. Since R minus M is adjacent side of the angle and R is the hypotenuse, we can use cosine I over 2 equal to R minus M over R. So R minus M is equal to R cosine I over 2, and M is equal to R minus R cos I over 2. So to simplify, R is 1 minus cos I over 2. So that would be for the middle ordinate. Next is the external distance E, the distance from the PI to the middle point of the curvature. And we can solve this using your actually write this. Yeah. So it's r plus e. This is r, and this is I over 2. We can solve using, we can apply secant I over 2 equals r plus e over r. So r plus e is equal to r secant I over 2. E is equal to r sec I over 2 minus r. And to simplify, r is secant I over 2 minus 1. So that would be for the external distance. So the long chord is the distance from PC, is the horizontal distance from PC to PT, and we can derive the formula from this figure. This is C over 2, this is R, and this is I over 2. So we can derive the formula using sine I over 2 is equal to C over 2 over R. So C over 2 is equal to R sine I over 2. So multiply both sides by 2, we have C is equal to 2 R sine I over 2. That's the formula for long chord. So the length of the curve is given by the formula LC is equals to R theta, where theta is the same with R is pi over 180. So that would be for the length of the curve. So we have an example here. The intersection angle of a 4-degree curve is 55 degrees 25 minutes, and the PC is located at station 238 plus 44.75. So we have to determine the length of the curve, the station of the PT, deflection angles, and the chord lengths for setting out the curve at all stations from PC. So the given where the intersection angle or the angles are 55 degrees 25 minutes, the degree of curvature is 4 degrees, station of PC is 238 plus 44.75, and we have to find for the length of curve as the APT, deflection angles, the given station, and C for the stations all stations from the PC. Sorry. So to solve for LC, first we have to find the radius using the formula I discussed earlier. So we can use R is equal to 5729.6 over degree of curvature, where it's equal to 5729.6 over 4. So R is equal to 1432.4 feet. So using the formula for LC, since there was a given angle, which is 55 degrees 25 minutes, it's equivalent to 55.4167. Formula for LC is R theta pi over 180. Since we already solved for R, we have 1432.4 times the angle 55.4167 times pi over 180. We have the length of curve is 1385.42. So the stationing of PT is equal to the stationing of PC plus the solved LC, since we already solved for LC and there's a given stationing for PC, so that would be 238.44, plus 4475 plus 13 plus 85.42, which is equal to 252 point plus 30.17. So that would be our station for PT. So the question in the problem did not specify what station we should get the deflection angle. However, the solution in the SIM indicated station 239. So to get the angle, we must first get the difference between STA 239 minus the station from PC to provide a value for LC. So since we already have station for PC, which is 238 plus 44.75, which is 55.25 feet, and using the formula for LC, we can now compute for the deflection angle using this formula. So LC is 55.25, so the answer would be 2.210 degrees. And to get the deflection angle, the formula is central angle divided by 2, which is equal to 1.105 degrees, or 1 degree 16 minutes and 18 seconds. So the problem asked for the value of the chord length at the whole station from PC using the degree of curvature. C is equal to, so C is equal to 2 times 1432.4 sine 4 degrees over 2. So we have C is equal to 99.98 feet. So note that the deflection angle of PT is half the intersection angle of the tangent, which is 1/2 times 55.4167, which is equal to 27 degrees, 42 minutes, and 30 seconds. So here are the computed deflection angles with its respective chord lengths. This can be available in the same. Now we are here in compound curves. So compound curves consist of two or more simple curves in succession turning in the same direction with any two successive curves having a common tangent point. And these curves are used mainly to obtain desirable shapes of the horizontal alignment, particularly at grade intersections, ramps of interchanges, and highway sections in difficult topographic areas. And to avoid abrupt changes in the alignment, the radii of any two consecutive simple curves that form a compound curve should not be widely different. And Aashto recommends that the ratio of the flatter radius to the sharper radius at intersections should not be greater than 2:1, so drivers can adjust to sudden changes in the curvature and speed. So as you can see, compound curve is a combination of two simple curves with a center of curvature on the same side of the curve. And the point where the two curves meet is called as the point of compound curve. And the intersection angle of the compound curve, this one, is the summation of the angles of the simple curve, which are this. So the only difference is the PCC and this one, which is called as tangent length of compound curve. And tangent length of compound curve is the summation of T1 plus VG. So I'm going to discuss how to get VG. So this table is for the lengths of circular arc for different compound curve radii. There are minimum length of circular arc, which indicates the acceptable and the desirable circular arc length. So these are the formulas for the simple curves. We have the intersection angle, which is the summation of the intersection angles from the two simple curves, and P1, we already know this from the previous. And to get this, we have, so we can solve for VG and VH using the figure from the compound curve. So this would be it. And then since this is an oblique triangle, we can use sine law to solve for the values of VG and VH. So VG is sine this angle, since it's the opposite angle, is equal to T1 plus T2 over 180 minus the intersection angle of the compound curve, which is also equal to VH over sine of the first intersection angle of the simple curve. So example, illustrate a compound curve that is to be set out at a highway intersection. If the point of compound curve is located at station 565, determine the deflection angle for setting out the curve. So to determine the deflection angles, we must first solve for the length of the curves. And the given are, R1 is equal to 500 feet, R2 is 350 feet. The first intersection angle for the first simple curve is 34, I2 is 26, and the total intersection or the compound curve intersection angle is 60 degrees, and the station for PCC is 565 plus 35. So for the length of horizontal curve of 50 feet radius, LC is equal to 296.71 feet, and for the length of curve of 350 feet radius, LC is equal to 158.82 feet. So therefore the station of PC is equal to 565 plus 35.00 minus 2 plus 96.71 equals 562 plus 28.29, and the station PT is equal to the station of PCC plus the solved LC2, which is equal to 566 plus 93.82. To solve for the deflection angle for r equals 500 feet, deflection angle at station 53 from station PC is solved by their difference, which is equal to 61.71, and 61.71 can be used to solve for the theta, which is 7.07 degrees. And so now we can solve for the diffraction angle, which is 3 degrees 32 minutes and 8 seconds. For station 566, the diffraction angle is solved by getting the length of the curve from station PCC to station 566, which is 65 feet. Using again the formula getting the deflection angle, we have 5 degrees, 19 minutes, and 16 seconds. Lastly, this is the table for the computed deflection angles of 500 and 350 feet radius of the curvature and its corresponding chord lengths. That's it, guys. Hope you learned something again. I am Sheena Barredo. Bye.